Embracing the unknown: uncertainty in artificial intelligence. Artificial intelligence, or AI, has made remarkable strides, mimicking human intelligence in various domains. From self-driving cars to medical diagnosis, AI systems are transforming our world. However, a fundamental challenge remains. Uncertainty. The real world is inherently unpredictable, and AI systems must learn to navigate this uncertainty to make reliable decisions. Imagine a self-driving car navigating a busy intersection. Pedestrians might suddenly cross the road, or another car might make an unexpected turn. The AI system must process this uncertain information and make split-second decisions to ensure safety. Similarly, in medical diagnosis, doctors often face incomplete or ambiguous patient data. An AI system assisting with diagnosis must account for this uncertainty to provide accurate and reliable recommendations. Quantifying uncertainty is crucial for building trustworthy and robust AI systems. By acknowledging and representing uncertainty, AI systems can make more informed decisions, provide more reliable predictions, and better adapt to changing environments. In the following sections, we will delve deeper into the different types of uncertainty, how they can be represented and reasoned with, and their practical applications in various fields. Unveiling the faces of uncertainty: epistemic, aleatory, and ambiguity. These three types of uncertainty play a significant role in the world of artificial intelligence and data science. Uncertainty is not a monolithic concept. It is a multifaceted phenomenon that can be broken down into different categories, each with its own unique characteristics and implications. It manifests in different forms, each with unique characteristics and implications for AI systems. Recognizing these forms is essential for developing robust AI models. Understanding these different types of uncertainty is crucial for developing effective methods to represent and reason with them. This understanding helps in creating more reliable and accurate AI systems. Epistemic uncertainty stems from our lack of knowledge about the world. It is the uncertainty that arises due to incomplete information or gaps in our understanding. It arises from incomplete data, noisy observations, or limitations in our models. This type of uncertainty can often be reduced by gathering more data or improving our models. For example, imagine an AI system trained to identify different species of birds. The system relies on the data it has been trained on to make accurate identifications. If the system encounters a bird species it has never seen before, it will experience epistemic uncertainty. This is because the system lacks the necessary information to make a confident identification. Aleatory uncertainty, also known as statistical uncertainty, arises from the inherent randomness of events. This type of uncertainty is intrinsic to the system and cannot be eliminated. Even with perfect knowledge of the underlying system, we cannot predict the outcome of a coin toss with certainty. The randomness is an inherent part of the process. This type of uncertainty is inherent to the system and cannot be reduced by gathering more data. It is a fundamental aspect of probabilistic events. Ambiguity refers to uncertainty arising from multiple possible interpretations of the same information. This type of uncertainty is common in natural language processing. For instance, the phrase "I saw a bat" could refer to a nocturnal flying mammal or a piece of sports equipment. The context in which the phrase is used determines its meaning. Ambiguity often arises in natural language processing, where the same word can have multiple meanings depending on the context. This makes it challenging for AI systems to accurately interpret and process language. Understanding the different types of uncertainty is crucial for developing appropriate methods to represent and reason with them. By recognizing and addressing these uncertainties, we can create more robust and reliable AI systems. In the next section, we will explore different mathematical frameworks for representing uncertainty in AI systems. These frameworks will help us better understand and manage the uncertainties we encounter in AI and data science. Taming uncertainty, probability, fuzzy logic, and Dempster-Shafer theory. In the ever-evolving field of artificial intelligence, managing uncertainty is a critical challenge that researchers and practitioners face daily. Representing uncertainty mathematically is crucial for AI systems to reason and make decisions under uncertainty. Without a robust framework to handle uncertainty, AI systems would struggle to function effectively in real-world scenarios, where data is often incomplete or ambiguous. Several frameworks have been developed to quantify and manipulate uncertainty, each with its strengths and limitations. These frameworks provide the mathematical tools necessary to model uncertainty and make informed decisions based on available data. Probability theory is a well-established framework for representing uncertainty. It has been the cornerstone of statistical reasoning and decision-making for centuries, providing a solid foundation for many AI applications. It assigns a numerical probability to each possible outcome, representing the degree of belief in its occurrence. This numerical representation allows for precise calculations and predictions based on the likelihood of various events. For instance, a weather forecasting AI might predict a 70% chance of rain tomorrow. This prediction is based on historical data, current weather conditions, and complex mathematical models that calculate the probability of rain. Probability theory provides a powerful toolkit for reasoning with uncertainty, including Bayesian networks and other probabilistic graphical models. These tools enable AI systems to update their beliefs and make decisions based on new evidence. Fuzzy logic offers an alternative approach to representing uncertainty, particularly vagueness in human language and reasoning. Unlike traditional binary logic, which classifies statements as either true or false, fuzzy logic allows for degrees of truth. Instead of assigning crisp probabilities, fuzzy logic uses degrees of membership to represent the extent to which an element belongs to a set. This approach is particularly useful in situations where concepts are not black and white, but rather shades of gray. For example, a fuzzy logic system might represent the temperature as warm to a certain degree rather than assigning a precise temperature value. This allows for more flexible and human-like reasoning in AI systems. Dempster-Shafer Theory, or DST, is a generalization of probability theory that allows for representing ignorance or lack of information. It provides a framework for combining evidence from different sources and making decisions based on the combined evidence. DST uses belief functions to express the degree of belief in a proposition, considering both evidence, supporting and contradicting it. This allows for a more nuanced representation of uncertainty, especially in complex and uncertain environments. This framework is particularly useful in situations with incomplete or conflicting information, where assigning precise probabilities is challenging. By allowing for partial belief and uncertainty, DST provides a more flexible approach to decision-making. The choice of uncertainty representation depends on the specific application and the nature of uncertainty involved. Each framework has its advantages and is suited to different types of problems and data. In the next section, we will explore how AI systems use these frameworks to reason with uncertainty and make decisions. By understanding and leveraging these mathematical tools, AI can navigate the complexities of the real world with greater accuracy and reliability. Navigating the unknown. Reasoning with uncertainty in AI. Representing uncertainty is only the first step. It involves quantifying the unknowns and understanding the limitations of the data we have. AI systems need to reason with this uncertainty to make informed decisions and predictions. This means they must be able to process incomplete, noisy, or ambiguous data and still arrive at useful conclusions. This requires sophisticated algorithms and techniques to process uncertain information and derive meaningful conclusions. These algorithms must be robust enough to handle the variability and unpredictability inherent in real-world data. Bayesian networks are graphical models that represent probabilistic relationships between variables. They are particularly powerful because they can model complex dependencies and update these models as new data becomes available. They allow for efficient inference and decision-making under uncertainty by updating beliefs based on new evidence. This dynamic updating process is crucial for applications where conditions can change rapidly. For example, a medical diagnosis system can use a Bayesian network to calculate the probability of a disease given a patient's symptoms and test results. This helps doctors make more accurate diagnoses and tailor treatments to individual patients. Dempster-Shafer Theory provides a framework for combining evidence from multiple sources even when they are conflicting or incomplete. This theory is particularly useful in scenarios where data sources may not always agree. It uses a combination rule to aggregate belief functions and update the overall belief in a proposition. This allows for a more nuanced understanding of the situation, taking into account the varying degrees of certainty from different sources. This is particularly useful in applications like sensor fusion, where data from multiple sensors need to be combined to make accurate inferences. For instance, in autonomous vehicles, sensor fusion helps integrate data from cameras, radar, and LiDAR to create a comprehensive understanding of the environment. Fuzzy logic offers a way to reason with vague or imprecise information. Unlike traditional binary logic, which deals with true or false values, fuzzy logic allows for degrees of truth. Fuzzy inference systems use fuzzy rules and membership functions to map inputs to outputs, allowing for more human-like reasoning in situations where precise numerical values are unavailable or irrelevant. This makes them ideal for applications where human intuition and experience play a significant role. For example, a control system for a washing machine can use fuzzy logic to adjust the washing cycle based on the perceived dirtiness of the clothes. This results in more efficient and effective cleaning tailored to the specific needs of each load. These techniques allow AI systems to navigate uncertainty effectively, making more informed decisions and providing more reliable predictions. By incorporating methods like Bayesian Networks, Dempster-Shafer Theory, and fuzzy logic, AI can handle the complexities and ambiguities of real-world data. In the following sections, we will explore specific applications of uncertainty quantification in various fields, highlighting its impact on real-world problems. From healthcare to autonomous systems, understanding and reasoning with uncertainty is key to advancing AI technology and its application.